The possibilities are not endless. This is the title of this video lesson for section 4.2 called Real Zeros, and the mastery objective is to have you be able to factor a polynomial completely. So let's talk about rational zeros. Rational zeros exist when we have polynomials that have integer coefficients. So in this lesson we're only going to look at polynomials with integer coefficients. And if there are rational zeros, there is a rational zero test that helps us try to figure out what the possible ones are. And if there are rational zeros of the form r over s, which is what rational numbers look like, remember, integer divided by an integer where s is not 0, then where they'd come from would be that the numerator, r, would be a factor of the constant term, and s is a factor of the leading coefficient. So really the leading coefficient and the constant term are used to try to figure out that list of possibilities. Again, this rational zero test does not find the rational zeros, it only generates a list of possibilities. So let's look at an example. If we want to find the rational zeros of this, we would look at the 7 and the 2. And the factors of 7 are 1 and 7. The factors of 2 are 1 and 2. What I do now is I generate kind of a fraction that would consist of the factors of the values of 1 and 7 kind of paired up with 1 and 2. And we have to consider both positive and negative varieties. So if I start to look at some possibilities, I'd be looking at 1 divided by 1. Negative 1 divided by 1, 7 divided by 1, and so on. So if we look at all those possibilities, I think you'd agree that the only possible rational zeros that would be generated from those would be 1 and its opposite, 7 and its opposite, that would be 7 divided by 1, 1 half and its opposite, negative 1 half, and 7 halves and negative 7 halves. So that's the list we work with. When we look at a graphing calculator of what the graphing calculator gives us for a graph of this with that window, we would see that it looks as if there are 4 zeros, 4 real zeros, 4 places where this is crossing the axis. It looks like there's 2 here, 1 there, and 1 there. Now, we have this list to work with, so if we're only finding the rational zeros, we see that this one right here, which looks like it's 1, 2, 3, 4, 5, somewhere between 5 and 6, is not in this list. And if there's any one that's over here, it might be negative 1. And this one, if it's in this list, would be 1 half. So using our calculator's capability of evaluating the function at these values, we would evaluate using a table. You could do it other ways. Negative 1 produces 0. Yay, that means that it's a rational zero, and so does 1 half. So we found the 2 rational zeros. To find the rest of them, we'd again look at the graph and say that there are 2 more, and to find these 2 other zeros, which are not rational but irrational, we know that negative 1 and a half are zeros. So x plus 1 and x minus a half are factors. That's from the factor theorem. So if we factor out x plus 1 with synthetic division, we get this leftover polynomial right here, which means that x plus 1 times that is equal to this polynomial function right here. So now we take this factor, 2x cubed minus 9x squared minus 10x plus 7, and factor out x minus a half. So we're really trying to reduce our quartic polynomial down to an eventual quadratic, and here we go. If we factor out a half, we're left with 2x squared minus 8x minus 14. Here we have, again, just as in the last example, let me go back to that. You see this 0 right here. That kind of makes us feel real good that we found that we have factors and zeros. So again, a half is verified to be a 0. So we have this polynomial left over. We can factor out a 2. And here we have it factored so far. The other zeros must come from here. Not factorable, but we can find the zeros by using the quadratic formula. So if we use the quadratic formula, and here it is done out, you may want to pause this and examine and appreciate the beauty of the quadratic formula. It produces 2 plus or minus the square root of 11. So this polynomial has 2 rational zeros and 2 irrational zeros. Now we can kind of use this idea to factor polynomials completely. We begin with the rational zero test, and again looking at 3 and 1, the leading coefficient. That would only generate these possible rational zeros. When we look at the graph, we see that it looks like it's touching the axis right here at 1 and at 3. So it looks as if x minus 1 and x minus 3 are factors. How you would get this is, if just like we just did, if you would use synthetic division and factor out x minus 1 by placing a 1 in that box, and then taking the leftover quotient and doing that with 3, you'd have this polynomial left over. Now, is that factorable? Well, how you can factor this is you have to take a shot at maybe one of these two zeros, 1 or 3, might be a factor of this. You might remember from Algebra 2, when the graph crosses or touches the axis like it does here, that means that there might be a multiplicity of 2. So we try 1 again, and 1 is factored out of this to give us this. And x squared plus 1 has no more factors, so we factored it completely. So that, in bold, is the complete factorization of this polynomial. And again, we use the rational zero test to kind of do that. Wow, a 7th degree polynomial, and we want to find all real zeros. Here is a graph, and if we look at the possible rational zeros from 4, factors of 4, which are 1, 2, and 4, and factors of 1, which are just 1, you would get 4, 2, and 1 in their positive and negative sense. So these are the only possible rational zeros. Well, this is not either one of those. Neither is this. This looks like 1 might be 1, and same with 2. So the two rational zeros are 1 and 2. And now I'd like to introduce you to this bounds test, this upper and lower bounds test. You see, we're looking at the graph, and as you might remember, the graphing method of solving solutions is not the best, because who knows if here we have a curve which looks like it's going up and turning around and coming down, up, through, back, touches. But how do we know it might not be outside of this window coming back down? Just like over here, it might do this. So this bounds test helps us kind of find the lowest possible value and the highest possible value for zeros. So what we do is we look and right here we say, okay, well, we have a pretty good feeling that -3, there are no zeros to the left of -3. So we take our polynomial and we do synthetic division with x plus 3. -3 would be our 0. And when we do that, we get the following. But what I want us to closely examine this, and you'll see that this is kind of interesting because you've got alternating signs. So this first sign would be x to the 6th because we divided x to the 7th by it. So these are the positive ones are the even powers, and the negative ones are the odds. When you put in numbers less than -3, they're negative. So all of these negative powers would actually produce positive values. These would all be positive values. These even powers, when you put in a value that's negative, would produce positive values. So all of this will produce positive values that you would be, here they are right here. So you'd be, if you put in these values, you're getting, everything here would be positive. and you're multiplying by a negative value. So this times this would be a negative. Plus you add on negative 1,000 and it's still negative. So we're told that these values will always be negative to the left of negative 3, which means it can't go back around and come back up. So now we say, well, what about over here? What's the furthest we have zeros over here? So we say, all right, let's check out and think that possibly the furthest value would be 1, 2, 3, 4. So if we look at 4, it produces all positive values in our quotient, which means that when we plug in values here greater than 4, this would be positive, and every one of these terms would be positive. So we're multiplying two positives together, get a positive, and add on 5,916, which means the value of our polynomial will be positive. So this tells us that 1 and negative 2 are rational zeros, and we know that there are no more zeros to the left of negative 3 or to the right of 4. So the other zeros must be this one and this one, and we can find those by using our calculator's capability. At least we know that we don't have to expand our window, we can just find them here. So they are, the other zeros would be, this would be the negative 2.6180 approximately. I don't have the approximate symbol, but that's approximately. And this one right here would be the negative 0.3820. So that's a look at how to find all zeros, how to factor completely. We will surely try a number of these in class. Feel free to review this again. As you can see, it's about 12 minutes. Review it again, stop it and pause and look at those examples again. Come in with any questions you might have, and we'll talk about them at the beginning of class before you try some examples.